Okay, so the last lecture in Chapter 9 is on this concept of odds ratios and confidence intervals for those odds ratios. So imagine we're looking at a tiny data set on flu vaccination. Obviously, we have a lot of data on how vaccination helps flu, so this isn't all of the data we have. This is just a tiny example data set to play around with. So you've got a treatment vaccine versus a control no vaccine, and then you're looking for the outcomes, whether or not the people involved in the study got the flu, yes or no. So we can lay out a contingency table like we've seen in the previous part of Chapter 9, and you could do a goodness of fit test, or a contingency test, I should say, which is a form of goodness of fit test, on this contingency table. For the null hypothesis that the vaccination is not associated with getting the flu. Okay, and you would not reject that null hypothesis. As it turns out, you can work through it on your own time if you'd like. I got a chi-square test statistic of 3.35 and a p-value of 0.067. There's 1 degree of freedom, because remember the degrees of freedom for the contingency test is the number of rows minus 1 times the number of columns minus 1. So there's 2 of each. So 2 minus 1 times 2 minus 1 is just 1. So it's a tiny data set, and we don't reject the null hypothesis. We can think about some summary stats that we might use for conveying to readers of the work where the data sort of leads us to believe what's going on. So if we think about p-hats or some probability of success, we could do that for each of the two categories, the treatment and control. We have to define what success means. Here we'll define that to be a flu equals no, or avoiding the flu. So the probability of flu equals no, given that you have the vaccine, that's p-hat sub v. We can only estimate that probability, right? And that's just the number of successes, 10, over the sample size for that group, so 10 over 13, and that gives us 0.769. And the probability of a success, avoiding the flu, given you didn't get the vaccine, is the p-hat for the non-vaccinated group. That's 13 over 28, so 13 successes over the sample size. That's considerably lower, 0.464. So we can see there's a trend in the data towards the vaccinated individuals avoiding the flu more successfully, but it wasn't significant because we had such a small sample size. What else can you do other than report these point estimates? Well, of course, we could do something like build a confidence interval for each of them. So if we wanted a 1 minus alpha times a 100% confidence interval, we'd use this formula, this Agresti-Cool formula that we've seen before, where the alpha level, the confidence for the interval, plays into the z statistic that we put in there. So if we're doing a 95% confidence interval, we look up the z statistic for 0.05, and that, as we've mentioned before, is 1.96. So there's a little recipe there for producing confidence intervals. I built a couple 95% confidence intervals for these two, and we see that they overlap, right? So we have a lower confidence interval for the true probability of avoiding the flu if you're not vaccinated, but that overlaps some with the vaccinated group in this area here. But we can't really reliably use the fact that two confidence intervals overlap with each other as an indication that there's not a statistically significant difference. So this confidence interval is useful, but it's only using a portion of the data for each of the confidence intervals, and it's kind of an indirect comparison to build two confidence intervals and try to directly say something about whether or not the hypothesis test would have rejected the null that these two parameters are equal to each other. So we know, because I told you I did the hypothesis test, that it was not significant, but we couldn't really tell based on this confidence interval. So this is a valid approach for building confidence intervals, and it's totally fine to do this, but often we want to compare effect sizes within a study and more succinctly summarize all of the data. So we'll often use, first of all, we'll often use what's called an odds of an event as opposed to the probability, and then we're going to see how this plays into an odds ratio for summarizing the whole study. So what is the odds of an event? It's just the probability that that happens divided by the probability that it doesn't happen, okay? So you hear things like 3-to-1 odds. If you have 3 times the probability, if the probability that it happens is 3 times larger than the probability that it doesn't happen. And odds are used in a lot of contexts like betting and gambling and stocks and things like that. It's just another way of summarizing a probability, because if you think about it, it's just a transformation of the probability. That's like p up here and 1 minus p. That's the probability that it doesn't happen. So the odds is just another scaling of the probability itself. If you know the odds, you can calculate the probability, and vice versa. But it's useful in several contexts. So one thing to bear in mind, of course, the probability scale goes from 0 to 1, inclusive of the endpoints. But the odds scale, since you can have a tiny, tiny probability in the denominator, you can get values approaching infinity. So it's not bounded on the right side. So bear that in mind when you're talking about odds. You can have an odds of 1,000 if the numerator is 1,000 times larger than the denominator. Okay, so that's what the odds of some event X are. Of course, when we work with real data, we don't get to see the true population odds, the odds that we would get if we had infinite data. We can just estimate the odds. So we have this hat here. We can estimate the odds as p hat over 1 minus p hat, right? So on the previous slide, I was talking about p over 1 minus p, but we don't know those population parameters exactly, so we're going to do the thing that we often do in stats, which is we're going to plug in estimates for them. Okay, so how would we do this, work through these calculations for this example I was looking at before? Well, previously I had shown you the table and I'd showed you these calculations right here for the two p hats, the p hat for the vaccinated group and the p hat for the non-vaccinated group. If we just work through the vaccinated group, the odds on the numerator, success was avoiding the flu, so it was 10 over 13, avoided the flu, and then failures was 3 over 13. So we notice that in the numerator and denominator we have fractions, and they have the same denominator of those fractions, so they cross out. So the odds is just 10 over 3, which is 3.3. So it ends up just being successes divided by the number of failures. Now you can only do this calculation if you have non-zero numbers for your failures, otherwise you'll get an infinite odds, which is your point estimate, but not really very reliable one. Okay, so for the non-vaccinated group, the same thing plays out. 13 out of 28 was the probability of success. That's our numerator, but 15 out of 28 is the failures over the total sample size. And once again, the sample size cancels out, so it's just 13 over 15, which is shown here in the table, 13 over 15. So there, the odds is less than 1, 0.867, so you can see that it's more probable that the event does not occur. When the odds is less than 1, then the probability of a failure is higher than the probability of success. When the odds are greater than 1, then you know the probability of success is higher than the probability of failure. Okay, so we can see that there's a difference. Once again, you can see that there's more success associated with the vaccination group, where success is the flu equals no events. So this may seem like a kind of silly thing to do. We've just rescaled probabilities, and it doesn't really give us any new information. Well, it turns out we can summarize the entire table. So the odds for the vaccination is summarizing that information. The odds for the non-vaccinated group is summarizing that information. We can summarize the whole raw table with what's called an odds ratio. It's a convenient way to compare the odds of the same events under two different conditions. So those are often the control and the treatment group. So the odds ratio for some event X is the odds of X in the treatment group divided by the odds of X in the control group. So for instance, our odds ratio for avoiding the flu, abbreviated OR, is the odds for the vaccinated group divided by the odds for the non-vaccinated group. And so once again, what's crucial is the success avoiding the flu. That's the same success in the vaccinated and the non-vaccinated group. So you're thinking about the same success and you're comparing the odds for each of those, and you produce an odds ratio. Okay. And of course, once again, we have the problem we always run into in stats. We don't know these population parameters. We can just estimate that. We can put a hat on OR by using the estimate of the odds for the vaccinated group and the estimate of the odds for the non-vaccinated group. Okay, so we can produce a point estimate for the odds ratio that's going to summarize all the information in the table in some sense. Okay, so we already said the odds of the vaccinated group was 3.33. The odds for the non-vaccinated group was 0.867. So we would just put those numbers in this fraction over here, this ratio, and we get a value of 3.846. It's also interesting to note that if we think about the odds originally being 10/3 there and 13/15 in the denominator, we've got fractions again, so we can think about like multiplying by 3 over 3 here. So then this 3 crosses out and this 3 stays. And we can think of multiplying by 15 over 15, right? It's okay to multiply by 1. You don't change the value. So in this case, the 15 crosses out here. And so we end up with the 15 multiplied by 10, so 10 over 15. And this 3 No, this is a mess, sorry about that. Multiply by 13. So it turns out that the quick way of calculating the odds is to multiply this cell times that cell and divide it by this, multiplied by that. And then you get the same number there, if you're just interested in the odds ratio. Okay, and so this summarizes what I just went through. If we want to estimate the odds ratio between treatment and control, we should lay out the table in a specific way. We put treatment in the left column, control in the right column, success on the top, and failure on the bottom. That's how I had it laid out the entire lecture thus far. I just didn't emphasize this too much. And then we can think of sort of nicknames for the variables, the data that shows up in each of those cells, A, B, C, D. And the odds ratio is A times D minus B times C. So you're sort of doing the cross multiplication here. A times D in the numerator, B times C in the denominator. Okay, so that's the shortcut method for calculating the odds ratio. It's totally fine to calculate the odds first and then calculate the odds ratio as the ratio of those odds. That's more close to the definition of what the odds ratio is. So that may be easier for you to remember, and that's fine to do that. You'll get the same number. All right, so that's the point estimate. But if we want to have something like a confidence interval on that and say, how confident are we in which plausible values the odds ratio they really are, well, it's a little tricky. And it turns out that the statisticians have figured out a nice formula, a fairly pleasing formula here. The square root of 1 on A plus 1 on B plus 1 on C plus 1 on D, where these are the 4 data points that we've seen. But that doesn't give us the standard error of the odds ratio. Instead, it gives us the standard error of the natural logarithm of the odds ratio. So just, turns out that the math gods have made this relationship follow this behavior here. Remember, there is a definition of a standard error. The standard error is the standard deviation of the sampling distribution. So if you plot a whole bunch of odds ratios and you plot their sampling distribution from repeated studies, it's kind of hard to describe, but if you take the logarithm of each of them and plot that, then you get something that looks a lot more like a normal distribution with this particular standard deviation. So that is the standard error that we can actually calculate. Okay, so if we want to produce a 1 minus alpha times 100% confidence interval for the log odds ratio, we just go with our point estimate of the log odds ratio. So that's the point estimate of the odds ratio, and we take the natural logarithm of that, plus or minus a z statistic where the alpha level here is determined by what kind of confidence interval we're building. So 1.96 for a 95% confidence interval, for example. And then we multiply that times the standard error of the log of the odds ratio, this formula here, which we can calculate from our data. So this is really similar to how we were calculating confidence intervals before. We've got a point estimate, plus or minus, a z-score, and a standard error. It's just a different form of standard error than we've seen before. All right, so let's apply this to our example here. We already said that the odds ratio, the point estimate of that was 3.846. Okay, what's the standard error? Well, it'd be nice if we could calculate the standard error for the odds ratio, but we have to calculate the standard error for the log of the odds ratio using that formula that I just showed you on the previous slide. So we're just putting 1 over 10 plus 1 over 13, all of the numbers at the table. This is A, this is B, this is C, and this is D. So it doesn't matter what order they are for this particular formula because they all just get put on the denominator of these fractions down here, 1/10, 1/13, 1/3, and 1/15. So these are the numbers expressed in terms of decimals. You notice that 1/3, of course, the smallest number in the table has, when you put that in the denominator, that's the largest term in this standard error, and the total standard error is a lot closer to this larger term than these other ones where you have large sample sizes of 15. This becomes sort of a negligible contribution to the standard error, which makes sense because remember, when we have small sample sizes, we have large standard errors. So the small sample size for any part of this table is going to kind of dominate the standard error. So anyway, 0.577, we take the square root of that, and I get a standard error of 0.76 for this example. Okay? So that tells us something about the confidence of not exactly the odds ratio, but the log of the odds ratio. So putting this all together, we've got our point estimate for the odds ratio. We've got a standard error for the log of the odds ratio. We can build a 95% confidence interval or 99% confidence interval, whatever kind of confidence interval, using this formula that I already discussed. So if we want to build a 95% confidence interval, remember the z-stat there is 1.96, but we need to center it around the point estimate of the log of the odds ratio, not the odds ratio. So not this 3.846, but the natural log of 3.846, which ends up being 1.347. So that's going to be the center point of our confidence interval. So the log of the odds ratio estimate, so it's a hat here because we estimated from the real data, is 1.347. Standard error, as I said before, was 0.76. So if we take that log of the odds ratio and we subtract 1.96 times the standard error, we get this number here, negative 0.1416. And if we take that same initial part, the same point estimate, take the log of that and add 1.96 times the same standard error, then we get 2.835. And what that's saying is that we can be 95% confident that the true log of the odds ratio, so there's no hat here, we're making a statement about a parameter of the population, is between negative 0.1416 and positive 2.834. Okay? So, no one really likes dealing with logs unless they have to, so what we would often do is express that in terms of the odds ratio to be more friendly to our readers. So there's the confidence interval I just showed you. Well, if we want to put it in terms of the odds ratio, we can think about how to invert the log function. So the exponential function, e raised to some power, that's the inverse of the log function. So if we take log OR, if we take e to the power log OR, we just get OR because the e and the natural logarithm cancel out, right? So we're going to make our confidence interval valid, we're going to do that operation to every endpoint of this as well. So e to this lower endpoint and e to the upper endpoint. So in our calculator, it may show up as exp on your calculator. You can plug in these numbers and exponentiate them. I get 0.868 for the lower bound and 17.04 for the upper bound. So we're 95% confident that the odds ratio falls in that range here. And so that's how we can finally, in the end, through several steps, produce a confidence interval for the odds ratio. So I know that's a lot of mathematical steps and looks a little tedious. This whole lecture really kind of boils down to remembering that general rule for a 95% confidence intervals and these special cases. So how to calculate an odds ratio itself from the table, how to calculate the standard error for the logarithm of the odds ratio, and then you should be able to build in a 95% confidence interval or 99% confidence interval using the recipe that we've showed you before. I should also point out that if we think about this on the number line, it goes from 0.868, here's 1, goes all the way up to 17, this really large number up here, 17.04. The fact that 1 is in the confidence interval means that we can't reject the idea that the odds ratio is 1. So the odds ratio is 1 is the null hypothesis that the treatment does not change the probability of success, right? So if I go back several slides to the definition of what an odds ratio is, it's the odds in the treatment and the odds in the control. And if the true population is, the treatment makes no effect, then the odds ratio would have a value of 1. You'd have the same success probability in the treatment and control. So when we look at a confidence interval for the odds ratio, we usually are looking for whether or not 1 is in that interval. And if 1's in the interval, we would not reject the null hypothesis that this treatment has no effect on success rate. And so that's consistent with the hypothesis testing result I showed you at the very end of at the very beginning of the lecture. The fact that 1 is in this confidence interval, it's inside this confidence interval, means that we would not reject the hypothesis that vaccination doesn't have an effect on flu. Of course, that's only true if you have this really tiny data set. A larger data set will tell you that flu vaccination is quite effective, so go get your flu vaccination. That's the end of this lecture. All right.